Hey everyone. In this video, I'm going to give you an overview of the major themes of our textbook, Regression and Other Stories, that we will follow throughout this semester. So, Regression and Other Stories provides a broad kind of introduction into statistical inference. And it starts with a couple of challenges or major challenges of statistical inference that we can address using regression techniques. So, what are these challenges of statistical inference? Um, First of all, one challenge that we talked about at length in POL Sci 701 in the previous semester is this idea of generalizing from sample to population. So usually we cannot observe our entire population that we want to study. We draw a sample, ideally a random sample, and we're trying to generalize from that sample to the population. And that's one of the key goals or key challenges of statistical inference, right? Usually that problem is most associated with the survey sampling because it's most obvious in that context that we have some finite sample of a broader population that we would try to generalize to. But actually this arises in nearly every application of statistical inference, that we have some population that is not fully observed and we have some sample of sorts. The second challenge of statistical inference is generalizing from treatment to control group. And that's the key issue of causal inference that we also discussed last semester, which ultimately consists of comparing a treatment group and a control group. And ideally, this treatment group and the control group are kind of equal on all other characteristics except for the administration of the treatment or not the lack of the treatment, the control group, right? So in order to make this comparison between the treatment and the control group, in order to be sure that they're kind of balanced on all potential confounding factors, of course, we can use randomized control trials, as we discussed in the last semester. But sometimes it's either not possible to have a perfect experiment, or there are other reasons why there might be potential pre-treatment confounders. And regression is one way ultimately to adjust for these imbalances between the treatment and the control group. Okay. The third challenge of statistical inference is generalizing from observed measurements to the underlying constructs of interest. And this is a key issue that is often a little bit ignored because ultimately what we're talking about here is kind of this issue of measurement and to what extent we're actually capturing the, for example, theoretical constructs that we're ultimately interested in, right? So oftentimes our data do not really record exactly what we ideally would like to study. We use proxies, we use certain measurement constructs and surveys and so on. And so another issue or challenge of statistical inference is to generalize from the measurement that we can actually observe to the underlying theoretical construct of interest that we ultimately care about. Okay, so those are the three kind of main challenges of statistical inference, and the key insight and the key kind of theme of the book is that all these issues, and I alluded to this to some extent, can be framed as problems of prediction, right? So when we generalize from a sample to the population, ultimately this is a prediction problem where we have a sample that we want to use to make a prediction about what the population would look like. Similarly, if we're generalizing from treatment to control group, we can think about this in terms of a prediction in a sense that we are adjusting between imbalances, or we're adjusting for imbalances between the treatment group and the control group by kind of predicting what the treatment group would look like in a hypothetical scenario if that group hadn't received the treatment, or the other way around, predicting what the control group looked like in the hypothetical scenario if observations in the control group actually received the treatment. Okay, so all these challenges can be framed as problems of prediction, and regression is ultimately an incredibly useful tool to make predictions, right? And also to quantify the uncertainty around these predictions, conditional on a set of covariates. Okay. So overall, statistical inference, as we discussed in the past semester at length, is about basically using mathematical tools to make general claims from particular data. We observe some subset of data and we want to generalize or make generalizing claims. And regression ultimately helps us to make those claims conditional on covariates that we do observe. Okay. So what are the key skills that you will learn in this class, kind of going beyond what we talked about in the previous semester? The first thing is we already talked a little bit about regression models, but we'll kind of take a deeper dive and really understand regression models. And kind of we start from this basic idea of kind of just predicting an outcome of a continuous variable from a set of predictors. Starting with a simple kind of like straight line fit. But then we're moving beyond this basic framework to non-linear generalizations. We're going to talk about generalized linear models and other types of transformations to kind of build on the basic framework. Okay. And then we'll practice a lot using our studio, kind of the idea of how to construct our regression models, right? So how do we, what kind of variables do we want to include? How do we have to transform these variables? How should we constrain them? The regression framework is extremely flexible and essentially open-ended. And so we will go at length through a lot of different practical examples to learn how we can actually come up with a modeling strategy for a specific substantive problem at hand. Okay. Then the next step is, of course, fitting regression models to the data. After we, come up with our regression models, we have to fit it to the data. As I mentioned before, and as we've done in the past semester, we'll do this using R in our studio. And I'll talk more about more specific packages going forward. And then another thing that is really, really important to me, and I really like that this is an emphasis in this book as well, is that we will talk about displaying and interpreting the results, right? So we're also going to talk a lot about visualization and how to ultimately communicate the findings, the scientific findings that you have to the audience that you ultimately want to speak to, right? And this is a key point, rather than just printing regression tables page after page. We kind of want to think about what are the key comparisons that we want to look at, what are the key insights that we can gather from the data that we have, whether it's descriptive or whether it's in the context of an experiment, and how can we communicate these most effectively. And we'll talk at length about that as well, and get started with it this week actually. Okay. So just to go back to one example that we talked about last semester, this was an example in the EMI book, and specifically what we're looking at here was an interesting study where respondents in a survey were asked to rate the pictures of lawmakers or candidates who are running for office, for Congress, and were asked to rate their competence of these candidates. They were unknown to them. They didn't know the candidates themselves, and they were asked to just rate the relative competence of two pictures of people who ran for Congress, for example, right? And then what the researchers did in that study was they basically looked at the relationship between the relative competence scores of two pairs of candidates who are running for election and their actual vote margin in a later election, right? And they basically showed that there is a relationship between how competent, just by looking at the picture, how competent that person was, or one candidate was viewed relative to another, is related to the ultimate vote share, right? Which obviously brings up some interesting questions. But I just want to have this as a reference for us to talk about or kind of drive home this point of why do we learn regression? Why is regression kind of useful in the context of these challenges of inference that we discussed on the previous slide, right? So in general, regression is a method that allows us or researchers to summarize how predictions of average values of an outcome vary across individuals defined by some set of predictors. Okay, and that's a very kind of most basic definition of regression. We're looking at the some outcome variable, and we're just examining how the average value of that outcome is related to or varies across ranges of predictor values of predictors. Okay, and of course we can assume different functional forms and so on. But that's the basic framework. Okay, so why is this useful? Why can we how can we use that? Well, obviously we can use that to make predictions, right? So we can use existing observations, or we can use kind of the relationship that we observe to make predictions. For example, to forecast new data. So in the context of this interesting competence study, we could use the insights from this regression, the relationship that we observe, to make predictions about vote shares in an upcoming election, maybe even of candidates who haven't run yet, just based on the competence scores that we observe in a survey. That would be one way of leveraging regression in this context. We can also just explore associations, right? Sometimes we're not really interested in forecasting or making clear predictions, but we're just interested in summarizing how well one variable or a set of variables predicts some outcome, right? So in this context, of course, there's some theoretical interest in why competence is related to electoral success, and what ultimately, does that tell us about the way Congress elections for Congress work, how electoral success, what the determinants are, relative determinants are of electoral success. Of course, from a kind of democratic perspective, you would want competence or facial features and appearance to have no role at all, and ideally it should be about ideology, policy positions and proposals, and so kind of explaining and exploring the association with something non-political like perceived competence is important also from a theoretical perspective. Okay. The last third point, not the last point, third point, is extrapolation. And what we mean by here, not in the sense of prediction as I talked about previously, but extrapolating as extrapolating from one sample to some other population or some other sample, right? So basically we have here a sample based on races or electoral races where candidates were running for Congress, right? We could now kind of think about adjusting for differences between this sample and the for example, if this was based on a student sample rather than some representative sample of people who evaluated the competence scores or evaluated the perceived competence, or for example, we could try to extrapolate to other types of political or electoral races, right? So, for example, rather than candidates running for Congress, we could think about candidates running for governor, like gubernatorial races, right? So that would be one example of extrapolating from one kind of observed association to another sample or another population. And potentially there some differences between one sample and the other sample. And in order to make these adjustments, we can also use regression techniques, essentially. The last point, which is kind of one of the most important kind of uses of regression, is to estimate treatment effects, so causal inference, right? Estimating this effect of administering a treatment for one group as compared to a control group that didn't receive that treatment. And as I mentioned before, a key challenge in this context is ensuring that the treatment and control groups are ultimately comparable, that they're similar on average before exposure to the treatment. So except for that one group received the treatment and the other one didn't, both groups should be as comparable as possible, right? There should not be any systematic differences on any potential pre-treatment confounders, okay? And to the extent that there are these differences, we can use regression techniques to adjust for these differences between groups in order to provide a more valid causal estimate. And we'll go through that going forward at length as well, right? So overall, as we kind of build our regression models, there are a couple of major steps that we always go through for any type of statistical analysis. And specifically, there are 4 steps that we'll go through again and again. The first one, as I mentioned, is model building. And usually in this context, we'll start with simple linear models, with potentially just one predictor and one dependent variable. But then we will ultimately expand by adding additional predictors, adding interactions, adding including certain types of transformations, and kind of building a better fitting model based on that, okay? So obviously then the second step is, after kind of we build the model, we have to fit the model to our data. And in order to fit that model to our data, there are a lot of additional steps involved. Like data manipulation, setting up, programming, setting up the actual model, estimating those regression coefficients and their underlying uncertainties, ultimately to make probabilistic predictions, right? So all these kind of fall into this realm of model fitting, okay? And then third, after we fit the model, of course, we have to understand how well the model ultimately fits our data, right? So in order to understand these model fits, we have to, for example, use graphics or examine kind of the predictive accuracy of our model. Maybe we'll fake some, we'll simulate some fake data and see how well the regression model works with simulated fake data, or how well the data that we simulate based on our regression model kind of resembles what we know about, marginal distributions and so on. So there are a lot of different ways of understanding model fit and checking how well our model fits the data, and we'll go through those as well. And then lastly, of course, we need to criticize our model. No model is ever, perfect and potentially or takes into account all potential confounding factors and so on, right? So we have to be critical of the models that we build and be open in finding flaws. Think about assumptions, to what extent they're reasonable, to what extent they're questionable, and think about overall improvements or directions to improve our models, right? And so this is why one of the major components of your grade will be actually replicating other people's work and then working on improving that work, right? So the constructive criticism ultimately is a key step in any statistical analysis. But of course, the key point is that it has to be constructive, right? Another point that I should just briefly mention is, in the last semester we talked a little bit about this difference between kind of classical or frequentist approaches to statistical inference and Bayesian interpretation or Bayesian inference, right? And so we'll continue this discussion of these different kind of philosophical frameworks and how we interpret probabilities and how we interpret uncertainty around regression coefficients, because in contrast to the previous semester, which kind of looked at this more from a frequentist perspective, looking at sampling distributions, how to calculate standard errors, and so on, we will now, or at least Regression and Other Stories, the textbook takes a slightly different perspective and emphasizes the value of Bayesian inference. Okay, so we will kind of follow the book in that regard, but we will also kind of take a step back and look and compare kind of classical frequentist approaches as well. And I will give you some additional material kind of going a little bit beyond what is provided in the textbook as well, right? So overall, though, one, key kind of aspect of statistical inference in this process of model fitting and criticizing models and interpreting models is ultimately kind of making predictions and interpreting these predictions and crucially interpreting the uncertainty around these predictions, right? And so these uncertainties can ultimately be kind of interpreted from different methodological and philosophical frameworks, okay? And that's where this difference between classical or frequentist and Bayesian inference ultimately comes in, right? So in general, whether or not you're a frequentist statistician or a Bayesian statistician, there are some main questions for statistical inference that kind of feed into your analysis, right? The first one is ultimately what information is being used in your estimation process. So, for example, how was the data collected, or to what extent there was a selection process, what data was collected, what data wasn't available to be collected. But essentially, there can also be other sources of prior knowledge about the specific functional form and so on. Okay, potentially coming from sources that are other than your data. Okay. The second key question is what are the assumptions that are being made? Assumptions in this case mean, for example, the functional form of the relationship between x and y. Is this a linear relationship? And so on. But it also goes beyond that regarding assumptions about where the data was coming from, what the data generating process was, but also kind of the relevance of the measured data, to what extent the measured data actually tells us something about our concept of interest, for example, right? All those kind of feed into those assumptions, right? And then lastly, ultimately, how are the estimates and predictions interpreted? And that's kind of the crux and the key thing where classical and Bayesian inference ultimately diverges. There are other differences as well, but the key point is ultimately to what extent or how we ultimately interpret uncertainty. And as we talked a lot about in the past semester from kind of a frequentist perspective, we think about uncertainty as a process that we characterize over repeated sampling procedures, right? So we have one sample and we kind of think about how much uncertainty would there be in our estimates if we repeated our sampling procedure 1,000 times, and how much would our point estimate vary across these samples. And we use that as kind of a basis to characterize the uncertainty around our estimates, right? There's some fixed true value in the population. We take a sample. Every time we take a sample, there's a slight deviation, but the true value ultimately in the population is fixed, and that's how we characterize our uncertainty. From a Bayesian perspective, ultimately there's basically the true population value itself kind of follows a random variable. There's some distribution over that population value, and ultimately our probabilities are interpreted in a different way, in the sense that the probabilities represent kind of our belief of where this population value ultimately lies, right? And while this sounds a little bit abstract, we'll talk in more depth about this going forward. But for now, what is important to remember is that this Bayesian inference framework allows us to take into account, for example, external information or prior information about what we believe the parameter estimates are likely to be, for example. Okay, and how exactly that works, and we'll talk about this a little bit in the past semester, is basically by invoking Bayes' rules, where we not only look at the likelihood um, um, of our data, so how probable it is to observe our data given that some null hypothesis was true, which is kind of the focus on of this classical or frequentist framework. We can take into account prior information. So how probable was our hypothesis before observing the actual evidence, right? And we can combine this information, the likelihood and the prior, to form our posterior, which is ultimately telling us how probable is our hypothesis given the observed evidence. Okay. We'll get more into the detail of we'll talk more in detail about how exactly this works and how we can integrate this prior information throughout the semester. Okay, so in terms of kind of frameworks, ultimately, what is important to remember is that there's not a clearly right or wrong answer. It's not like frequentists are wrong and Bayesians are right, or the other way around. But there are trade-offs. This is a choice in terms of how you kind of think about probability and how you kind of interpret uncertainty around our estimates. And there are advantages and disadvantages going one way or another, right? For the authors of Regression and Other Stories, the benefits of using a Bayesian framework outweigh the costs, because we have a couple of advantages, namely the ability to take into account prior information, but also, for example, in contexts where you have small data sets, for example, or high variability, Bayesian inference allows you to ultimately provide more stable estimates, right? So in a lot of cases, as I said, with small data sets, or where there's a large amount of variability across observations, Bayesian estimation, by invoking kind of prior information, will provide you with more stable predictions that are more sensible, right? So it has practical advantages. There are other practical advantages, for example, when it comes to communicating your results and trying to kind of describe the uncertainty around your estimates. And we'll kind of show how it's relatively easy in the Bayesian framework to directly kind of visualize uncertainty around your estimates and around your predictions. And in frequentist approaches, of course, that's also possible, but it is oftentimes a little bit more cumbersome. Okay, so this was kind of a very broad overview of kind of fundamental discussion that we will kind of have throughout this semester in terms of kind of modeling in R. We will look and compare kind of both approaches. Again, I want to emphasize this is not like a question of right or wrong. This is a question of different kind of philosophical perspectives on probability. There are trade-offs. We'll talk about these trade-offs and we'll see how what the advantages of each kind of perspective ultimately are. Okay. So that's it for this video, the overview of kind of the major themes that we'll follow throughout this semester. I hope this kind of gave you a better sense of where we're going in the next couple of weeks. And in the next video, I'm going to show you a quick coding example where we're going to talk about estimating the effects of UN peacekeeping missions.